That faint band of light is the Milky Way, and running along it is a pattern of stars that form a cross. That's Cygnus the Swan. The head of the swan is a star called Albireo, and the tail is Deneb. See if you can find Albireo with the telescope, Jason.
The night sky makes us wonder about the universe and our role in it as human beings. How were stars and planets created? How old is the universe? Is there life beyond our solar system? Astronomers from all over the world use the Green Bank telescope to find some answers. While optical telescopes give us an enhanced view of the visible universe, radio telescopes provide a deeper look at the cosmos. Telescopes at the National Radio Astronomy Observatory capture and measure radio waves that are invisible to the human eye. All matter generates electromagnetic energy. Cosmic objects like planets and stars radiate energy across the electromagnetic spectrum. A tiny sliver of this energy is in the form of visible light, the colors from violet to red. Still, other forms of energy exist and differ only in their wavelength. Honeybees using ultraviolet vision see an inviting target in this flower. Light that is redder than red is called infrared. We feel its energy as heat. Much redder than infrared are the radio waves. While you can't see anything through a radio telescope, sensitive receivers and computers can. The goals of radio astronomy are similar to optical astronomy, to study the characteristics of objects emitting electromagnetic energy. Planets, exploded stars, clouds of gas, and distant galaxies all emit radio waves. Radio telescopes may not look like other telescopes, but they are similar. The large bowl-shaped dish is a mirror to radio waves. Radio waves reflect from the dish surface to a focus where the radio astronomer places a sensitive radio receiver instead of a camera. Like this neon sign, which glows a characteristic red, molecules glow in specific radio colors or wavelengths. By tuning a radio telescope to the right wavelength, astronomers can probe the chemistry of the Milky Way and other regions of the universe.
We're mapping the Milky Way galaxy using the spectral line of hydrogen. With radio waves, we can tell what things are made of by their different spectral lines. And hydrogen is one of the most common atoms in the universe. It's one of the simplest atoms. And it has a spectral line with a wavelength of 21 centimeters, a typical radio wavelength.
Mapping the hydrogen in the Milky Way has led astronomers to conclude that we live in a spiral galaxy, out in the galactic suburbs on a spiral arm. Radio astronomers have also peered into dark clouds where new stars are being formed. They have discovered that these clouds contain chemicals similar to those on Earth.
One of the things I study is star formation in the galaxy. And the regions that I like to look at are regions that are deep inside of molecular clouds. These regions are completely obscured optically. So if you were to point an optical telescope at some of these regions, you would just see blank sky. You wouldn't see anything at all. Whereas a radio telescope will see deep down into those clouds because the radio waves don't get absorbed by the gas in the same way that the optical waves do. So you can see regions of space, you can see regions of the galaxy that you can't see with an optical telescope.
Radio telescopes like the one at Green Bank, West Virginia, enable astronomers to cut through almost 30,000 light years of obscuring dust and observe the very heart of our galaxy. They reveal huge clouds of gas moving at tremendous speeds. Much farther in the universe than our own Milky Way, the Green Bank telescope reveals some of the brightest radio objects known. The smudges and dots in this view of the radio sky aren't the ordinary stars you see at night. Instead, they are galaxies and quasars. Galaxies and quasars 1, 5, or even 10 billion light years away. Detailed images of these powerful galaxies show extensive jets of subatomic particles spewing tens of thousands of light years into space at nearly the speed of light. Within the cores of radio galaxies and quasars, we suspect the existence of massive black holes, objects with a gravitational field so strong that not even light can escape. Radio astronomers can peer back to a time before stars and before galaxies when nothing filled the universe but the hot gases from the Big Bang. A trace of this event lingers as a faint radio signal permeating the universe. The Green Bank telescope may remind you of your TV satellite dish. But the GBT is millions of times more sensitive to incoming radio waves than your home electronics equipment. Imagine tuning in a typical radio station 10 miles away. The signal you receive will be only a few thousandths of a watt, but the Green Bank telescope detects radio waves from space that are a billion times weaker. Weak because of the vast distances they travel. Since radio waves from space are such weak signals, astronomers need large, very sensitive telescopes like the one at Green Bank to catch the waves. Just as a bigger bucket collects more raindrops, bigger radio telescopes collect more radio energy and can see farther. Its 100 by 110 meter steerable dish has an area of 2.3 acres. That could easily hold a football field. Weighing in at 17 million pounds and 485 feet tall, the GBT is the largest moving structure on land. Despite its size, the Green Bank telescope is incredibly accurate. The telescope can be pointed with an accuracy of 1 arcsecond. That's like being able to see the individual pepperoni on a pizza from 3 miles away. The telescope is designed to study radio waves ranging from 3 meters in wavelength to a tiny 3 millimeters in wavelength. In order to detect these smallest of radio waves, the surface of the Green Bank telescope must be perfect. Extremely sensitive lasers scan the surface and provide data to 2,000 motors that position the reflector panels to a precision of 1/10 of a millimeter. That's smaller than the period at the end of a sentence. The ability of the GBT to detect extremely faint signals is a blessing and also a curse. It means that it is sensitive to man-made radio signals as well.
Interference is a big problem in radio astronomy. It's a terrible problem that's getting worse and worse all the time. Interference is signals which come into the telescope, but they don't come from space. They come from artificial things like radars. Here's a line, for example, right here in my spectrum, which fortunately was a little bit spaced away, but it could just as well have come right on top of my signal. That line could come from a radar, maybe at an airport thousands of miles away, or it could come from somebody's cell phone or somebody's microwave oven just down the valley. It could even come from something like an electric fence or a car engine.
Both the design of the GBT and its location in Green Bank help to reduce interference. The Green Bank telescope is located in the National Radio Quiet Zone, a national preserve for radio astronomy. The Quiet Zone and surrounding mountains protect GBT receivers against most unwanted man-made interference. Perhaps the most interesting question the human species ever asks is, are we alone? Unable to travel interstellar distances, we have only one tool currently capable of answering this question: the radio telescope. From Green Bank, astronomer Frank Drake conducted the first radio frequency search for a beacon from other civilizations. In a way, Earth is also a radio beacon. Since Drake began the search for extraterrestrial intelligence, our own radio signals have been traveling into space at the speed of light. Faint echoes of early TV shows are now more than 50 light years away.
This is our Mayberry Knot Time class. Meets here every Tuesday.
If other civilizations are broadcasting signals like we are, radio telescopes could one day detect an extraterrestrial version of Andy Griffith. The search continues. Armed with groundbreaking technology, astronomers at Green Bank continue to make spectacular discoveries as they gaze ever deeper into space. The Green Bank Telescope, reaching new frontiers, from the solar system to the edge of the universe.